Hello and welcome back to Nunley Math. I am your host, Aaron Nunley. I want to thank you so much for joining us as we continue our exploration of using systems to solve application problems. In our last video, we talked about just some basic systems patterns, some simple application problems that could be modeled using systems, but we're going to work our way into much more specific problems that people tend to struggle with when they're learning about systems, specific applications that traditionally have been challenging for students. And I think a lot of the reason for that is we don't take the time to look at them one at a time and begin to examine and look for patterns. So you'll notice that the title of this lesson is Digit and Coin Problems. We'll talk about those two different patterns today, and then in the next couple of videos we're going to begin to talk about increasingly more and more challenging systems application problems, so that hopefully by the end we've done enough of these that you can begin to see the patterns that emerge, and so hopefully they will not be as complex as they have historically seemed. Now, what I am going to do is I am going to take you for just a moment back to elementary school. We're going to call this an elementary flashback, where we're going to look back at some questions you might have been asked early on in elementary school, and I want to see how they can relate to what we want to talk about today. In probably second or third or fourth grade, you probably had a teacher that asked you to write each number below in expanded form. And then they would give you something along the lines of a number like 81. And they wanted to understand if you could write 81 in other ways. Now, specifically when they're talking about expanded form, they're trying to see if students understand that a number in this position has a different value than the same number in this position. For example, when I see a number 8 written in this left position, it doesn't actually mean 8, it means 8 sets of 10 or 80. Whereas a 1 in the first place just means exactly what it says, a 1. And so in expanded form, you might write that out like this: 10 eighths and a 1, because anything in this second position, or the tens place, has a value of this many tens. Hopefully that's not unfamiliar or strange to you. We could do the same thing with a number like 29. If your teacher asked you to write the number 29 in expanded form, hopefully you would realize that this 2 actually has greater value than this 9, because this 2 is not just a 2, but it's 2 tens. So a 2 in this second position is actually a 20, which of course is greater than a 9, which is the value of this 9 in the ones position. And with 36, you would do something similar to that. This 3 does not have a value of 3. It has a value of 30, because since it is in the tens position, it is 3 tens. And of course, the 6 is all by itself over here. It actually has a value of 6. Do you remember doing this? At the time, it probably seemed pointless or kind of strange that a teacher would want you to write something in this form, when this form seems to be more complex or more complicated than this form. But the idea is to get us used to the idea of, or the fact that numbers positions give them a value or indicate the value of that number. So what I want us to do today is I want us to look at these 3 examples, and I want you to notice something. When we write this out, every example here has a 10 times the number in the tens position plus the number in the ones position. Same thing here, 10 times the number in the tens position plus the number in the ones position, 10 times the number in the tens position plus the number in the ones position, or 10 times the digit plus the other digit, 10 times the digit plus the other digit. I mention that because this can be represented as an algebraic pattern. Any 2-digit number can be expressed as 10 times x plus y, where x is the number in the tens place and y is the number in the ones place. So going back to our example of 81, 10 times x, notice x in this case would be an 8, it's the number in the tens position. 10 times x here is the 2, x is the number in the tens position. 10 times 3 here, the 3 is the number in the tens position. Plus y, the thing on the end, being the number in the ones position. Does that make sense? Think about that again. 10 times x plus y can express any number if this x is the number or digit in the tens place and this is the digit in the ones place. Take a look at this though. If I were to switch the 8 and the 1 from our first example, and instead of doing 10 times 8 plus 1, I did 10 times 1 plus 8, I get an 18. If I were to switch the 2 and the 9 and make it 10 times 9 plus 2, I'd get 92. And by switching the 3 and the 6, I'd get 10 times 6 plus 3, which is 63. Look at the numbers that are written here compared to the numbers that are written here. Notice the number that used to be an 81 is now an 18. The 29 has become a 92, and a 36 has become a 63. When you switch the location of the number, you switch which value is in the tens place and which value is in the one place, resulting in the reverse of the original number. Notice 81 is now written backwards as 18, 29 is written backwards as 92, 36 is now written backwards as 63. We can represent this algebraically as well. The reverse of any two-digit number can be expressed as 10 times the number in the ones place plus x, the number in the tens place. You might want to pause the video and look back at this and make sure that makes sense. If over here 3 is x and 6 is y, 10 times x plus y, or 10 times 3 plus 6, gives me 36. But 10 times the 6 plus the 3, 10 times the number in the y position plus the number in the x position, gives you the reverse. These two patterns become very, very important for us in the next couple of slides. Notice 10x plus y is any two-digit number. The reverse is always 10y plus x. Let's take a look at how we can use that. The sum of the digits of a two-digit number is 14. If the digits are reversed, the number is 36 greater than the original number. Find the original number. Just like in our previous video on systems, we're going to solve this the exact same way. We're going to define our variables. In this case, we're asked to find the original number, but the problem is about digits. The problem is about digits. Since we're dealing with a two-digit number, we're going to define the tens digit as an x and the ones digit as a y. Notice that's the same thing we did in the previous slide. And then we're going to start to look for which relationships are given to us. The first sentence is a digits sentence, and it says the sum of the digits is 14. If x and y are my digits, how would I express that? X plus y equals 14. My second sentence talks about what happens if I reverse the digits. Notice it says, if reversed, the new number is 36 greater than the original number. Here's where our digit patterns that we learned in the first slide come into play. If reversed, that new number, notice the expression is starting off with the reverse of our number. Do you remember the reverse pattern from the original slide? The reverse is always 10y plus x. Let's keep reading. If reversed, that new number, this 10y plus x, is always an equal sign, 36 greater than. 36 greater than. Notice it's 36 greater than is always addition, but the than changes the order of the addition, the original number. Well, the original number was 10x plus y. And if I'm going to be 36 greater than that, I should put a plus 36. Notice you now have a system. The first talks just about the digits. The second talks about what happens if I reverse the digits. I get the new, or reverse, is 36 more than the original. It might be worth writing down somewhere that 10x plus y is always the original number and 10y plus x is always the reverse of the number. Now, this is our system. We have two equations. I don't like this second one because it's fairly complex. I am going to go through and simplify it just a little bit. I'll do this relatively quickly. Using the property of equality, I'm going to subtract 10x from both sides and get this. I'm then going to use the property of equality again to get rid of the y, and I'm left with this. And then notice my x and y are on the same side. I'm going to go ahead and use the commutative property, and I'm going to rearrange this so that it is in standard form. Notice that this minus 9x becomes plus negative, and then I use the commutative property. And now I can solve my system. I have my original equation, x plus y equals 14. I have my new equation, negative 9x plus 9y equals 36, and I can solve that either using substitution or addition. Which way do you think is probably going to be easier? More than likely, since these are both in standard form, your best bet is to use the addition method, or elimination or linear combination, depending on which textbook you're working in. The linear combination or addition method says add the x's together, add the y's together, and try and get them to equal 0. But you'll notice when I add these, that does not occur. Because of that, I'm going to change the first equation using the property of equality. I'm going to multiply both sides by negative 9. That turns the first equation into negative 9x minus 9y equals negative 26. And the second equation into is still negative 9x plus 9y equals 36. When I add those together, notice that negative 9x and negative 9x make negative 18x, but this y term disappears and becomes a 0. You're left with negative 126 equals 36, and now, or negative 126 plus 36 equals negative 90, and then we just divide away the negative 18. Notice that your x, or your tens digit, is a 5. Now, I did do the solving process here fairly quickly. That is not the focus of this lesson. If you're struggling with the addition method, you might want to go back and watch our video on that. But suffice it to say that our attention here is primarily on setting up the equations. Once you know the first variable, x equals 5, we can pick either one of these original equations, plug in a 5 for x, and solve for y. That gives you the 9. The last thing you have to make sure you do is answer the question. If x is a 5, the tens digit, and y is a 9, that means the original number was 59. Now, 5 plus 9 does equal 14. If I were to reverse this, 95 is equal to 59 plus 36. And you can check your work pretty quickly and easily that way. If that made sense to you, I would recommend pausing the video and trying the second one on your own. It is very similar. You shouldn't have a whole lot of trouble with it. I'm going to just assume you've paused the video and tried that, and we're going to work this out again together quickly. Once again, in a digit problem, x is always my tens digit and y is always my ones digit. When I look for relationships, my digit equation is going to say the sum of the digits is 12. So x and y is 12. Then I can look at the second sentence, which talks about what happens if we reverse the digits. If reversed, the new number is 18 less than the original. Let's walk through that slowly. If we use the reverse is always 10y plus x. That is 18 less than the original. I know that less is subtraction, so I'm going to take the original number and then subtract the 18. I know the 18 is second because of the word than, and you get this equation. Once again, this is a little bit messy, so I'm going to use my property of equality to move the 10x. I'm going to use my property of equality to move my y. And then I'm going to make that minus 9x into a negative 9x and use my commutative property again. That means my system is x plus y is 12, and a negative 9x plus 9y equals 18. Just like before, since they're both in standard form, I am going to multiply through both of those, or through the first one. And that's going to give me negative 9x minus 9y equals negative 108. The second equation stays the same. When I use the addition method, the y's go away, leaving me with the negative 18x. And once again, this one happens to give me a 5. It's merely a coincidence that we've had a 5 twice in a row. That doesn't happen every time. I can pick either one of my original equations. I usually pick the easier one. Plug a 5 in for x, calculate y, and then answer the question. If 5 is my tens digit and 7 is my ones digit, the original number must have been a 57. Now, a couple things to point out. When we work with digits, it is very, very common for that second equation to be negative 9x plus 9y equals something, because we're always going to be using 10y and y. We're always going to be using 10x and x. So don't be surprised that this happens a lot. It makes it kind of nice because that tells us we can always multiply through the first equation. Well, most of the time multiply through the first equation by a negative 9 to get our variable to disappear. If you're really brave, instead of multiplying through the first equation by negative 9, you could go through and multiply through the second equation by 1/9. It does result in some smaller numbers, but it does involve some fraction work. The nice thing is about this problem, since we're dealing with digits, these will never come out as decimal values because you don't have a decimal value for a digit. If you end up with a decimal value, something has gone terribly wrong. That's the first of our two types for today. The second type is the coin problem. It's very similar in structure to the digit problems. That's why we teach them together. This one says, Cammie has some nickels and some dimes. The value of the coins is $1.65. There are 12 more nickels than there are dimes. How many of each kind of coin does she have? Just like always, we define our variables. The variable is always found in the question. How many of each kind of coin does Cammie have? The word each tells me that I'm going to have more than one unknown. In this case, we're talking about nickels and we're talking about dimes. Let's look for our two relationships. There is a sentence that talks about the quantity of our coins. It says there are 12 more nickels than dimes. Can you write that as an algebraic expression or equation? Hopefully you notice that n equals d plus 12. Now I will tell you a lot of people struggle with this phrase 10 more nickels or 12 more nickels because they think that they should take the 12 plus nickels. But if you read through it and ask yourself, what should I have more of? This says there are more nickels. So you need to make sure whatever equation you come up with, you end up with more nickels. You also have a value equation where you're not talking about the number of physical coins, but you're talking about how much they're worth. And in this case, you're told the value of the coins is $1.65. Now, remember, in most of the examples we've done, I have a tendency to put these two equations in the order they appear in the problem. I actually didn't do that this time because this idea of a quantity equation and a value equation is very common. It's actually the way that I structure all of my all of my coin problems, if I can possibly help it. And it's a habit I would suggest you get into. When I'm looking for my relationships, I don't always write these sentences out, but most of the time I will actually take the time to label which equation is which. I say that because when we talk about the quantity of coins, we're talking about N and D. But when we talk about the value of our coins, a nickel does not have a value of N. A nickel has a value of 0.05 N because it's 5 cents for every nickel. It's important to keep separate in your mind. The first equation, we're just talking about the number of coins. The second equation, we're talking about the value of those coins. So in the first equation, we're going to use N and D. In the second equation, we're going to use 5 cents for every nickel, and 10 cents for every dime has a value of $1.65. If you can learn to keep those two things separate in your mind, coin problems are not terribly difficult. Now, I don't necessarily like to deal with lots of decimals, so I'm going to use my property of equality to get rid of those, multiplying through by 100. That gives me 5n plus 10d equals 165. And that is your system. Now, in this case, you will notice that the n is already by itself. That means substitution is probably going to be easier. I can take the d plus 12 and plug it in anywhere I see an n. And I happen to see one down here. There it is, down here. So I'm going to take this second equation, the blue one, and I'm going to replace that n with a d plus 12. Now I have an equation that is in one variable. Distributive property, combine my d's, property of equality, the number of dimes is 7. Once you know the number of dimes, you just pick either of the two equations. I usually pick the easier one, n equals d plus 12. Plug in what you know, solve for what you don't, and make sure you answer the question. Notice that 7 dimes is 70 cents, 19 nickels is $1.95, or say is 95 cents. 95 cents plus 70 cents is your $1.65. Last one. This is a money problem as well. It's very similar to the coin problem. There were 411 people at a play. Admission was $5 for adults and $3.75 for children. The receipts were $1,978.75. How many adults and how many children attended? Notice the question tells us what our variables are. A is adults, C is children. I'm looking again for relationships. In this case, I have a number of people because I'm told there were 411 people at the play. If I look at my adults and children being a total of 411, you can come up with your first equation. The second equation is going to deal with the money that's brought in. Notice admission's $5 for adults and $3.75 for children. The receipts were $1,978.75. If we think of the $1,978.75 being the total amount of money, we bring in $5 for every adult, and we bring in $3.75 for every child, giving us a total of $1,978.75. Once again, that is your system. Both of those are in standard form, which means the addition method is probably going to be easiest. I'm going to multiply through that first equation by -5, giving you this. Keep my second equation the same. -5a and 5a become 0. -5c plus 375c is -1.25c. I subtract the totals and I end up with -76.75. Property of equality. There were 61 children at the play. Once you know the number of children, you pick either equation, plug it in, property of equality, and you're done. Always be sure to answer the question. Now, I can look at this and say 61 plus 350 is 411 people. It would take a little more work, but if I was allowed to use a calculator, I would just take 61 times $3.75 each, add that to 350 times $5 each, and see if it comes out as the 1978-75. Now, that was a lot of information all at once. Hopefully it wasn't lost on you. You got a chance to write that down. Again, if we can keep up with the patterns that emerge, these are all very similar to one another. If you define your variables well, most of your labor will be spent in this middle step, trying to create equations that have meaning. At this point, the actual solving the equation should be second nature, shouldn't be overly difficult for you. So make sure you're investing a lot of time in getting good, accurate models. As always, thank you for watching. Make sure you hit that like button. Leave us a comment in the comments section. Make sure you turn on your notifications so you don't miss anything that's coming up. Over the next couple of days, we're going to deal with some increasingly challenging application problems that can be solved by systems, some that are classic math problems that people have talked about for years and years. I think you're going to enjoy this. So, as always, you guys take care of yourself.